Hello, we are the Project Wearable team, which consists of the members Eric, Ken, Andrew, and Steven.
The original intention for this problem was to design a device so that we could help direct care workers in helping sustain injury from their daily tasks. Direct care workers are incredibly susceptible to back injury as they are constantly having to help move patients around, which can require awkward body movements. Our goal is to create a device which can track and monitor the positioning of the user's back to help ensure that they are not putting themselves at risk for injury.
Our plan was to strategically place sensors around various points around the body in order to map the user's posture. The system is a wearable device that houses 5 sensor units and a central hub communications unit that communicate through Wi-Fi. The image shows the location of where the sensors will be placed.
The concept of our design involves several ESP32 boards with MPU 6050s, where we would have one central hub along with multiple ESP32 boards constantly passing data into the hub. The logic and justification here is to be able to communicate the information of each section within each board to a central hub for data collection to determine how precise and accurate it will be when involving movements. Currently, as shown, the code is uploaded onto the ESP32 via Arduino, and as demoed, you can see how the data is being sent or communicated via Wi-Fi to the hub on the serial monitor.
The following modifications have been made to the system since the first prototype design. First and most importantly, the MPU 6050 accelerometer board was exchanged for the Adafruit BNO055, another accelerometer board that uses a 9-axis orientation instead of the 6-axis orientation used by the MPU 6050. The new accelerometer board will provide absolute orientation data, whereas the MPU 6050 only provides relative orientation data. This way, each time the devices are powered on, the sensor automatically calibrates to its geospatial position. This ensures consistent orientation readings no matter the initial conditions of when the devices are powered on. To ensure secure electrical connections, the accelerometer is then soldered into a PCB along with the microcontroller. Measurements of the board were taken to fit a 3D printed casing using a computer-aided design software. The boards are then mounted inside the casing to help protect from external forces and to make sure the accelerometer stays fixed while the user is moving about. Each device is then mounted into the newly designed harness. This new shirt-style harness captures the importance of securing the devices to the user at specific locations while increasing the simplicity and comfort of the user.
As for how the metrics are obtained, well, first off, the sensors are continually sending data to the hub via Wi-Fi. The hub sees the sensor number where it came from along with its respective data values. To help collect and clean up the data, we use a third-party tool called the Ardu spreadsheet. This tool separates what it sees in the serial monitor into columns and allows what it recorded to be saved directly into a CSV file. The CSV is further cleaned up by deleting any messages that may have entered the serial monitor during the recording and is then sorted so that the values are grouped together with the respective sensor number. In other words, sensor 1 values are sorted to be near other sensor 1 values. As you can see from this example graph, the data is broken down into 3 metrics. These include the degree of upright stance, the degree of squat, and the degree of spinal twist. This MATLAB code is what turns the organized CSV file into metrics. By inputting the CSV file into the code, it calculates the said metrics of squat, stance, and twist by assessing the values it received. For instance, comparing certain values it sees on the shoulder sensors with the leg sensors to calculate twist metric, and looking at how the leg sensors change in orientation to find the squat metric. These graphs are from the MATLAB code and show what we expect to see for each movement with respect to the metrics we are calculating. Of course, during the stand movement, all 3 metrics should stay the same. During the bend over movement, stance should show the biggest change, whereas the other 2 metrics stay relatively the same. During the squat movement, squat should show the greatest change, stance should show a bit of change, and twist should stay constant. During the twist movement, the twist metric should change based on the intensity of the twist, stance should show very little change, and squat should not change at all.
By running several trials within the system, we can conclude that our hardware and software are sufficient enough, since it is able to match the movement with the data of the desired metrics, thus allowing us for consistency among different users with different characteristics of the system. There are several plans and options for the future of this project. One of those options could be to add more metrics to the system in order to gain a more accurate picture of a user's movement. Another one of those options would be to expand the MATLAB code to assess risk injury of a user by gathering more data to separate into low risk and high risk, where then, if possible, an algorithm can be created to compare the user's movement to give a probability of injury. Lastly, another option or goal, to be precise, is to add insole pressure sensors under the user's feet to detect weight distribution as well as calculating the weight of an object being applied to the user.